Hello and welcome to Honors Function. In this video, we're going to be covering the average rate of change and the difference quotient of a function. In the previous two lectures, we looked at the intervals of increase and decrease of a function. This lecture and the next continues looking at the change in the outputs of a function. Let's begin. So let's consider a function that we call f with its graph, and let's take two input values, x1 and x2. Let's also denote f of x1 by y1 and f of x2 by y2. Okay, let's first define the total change of f over x1, x2. So how do we define the total change over the interval x1, x2? Very simply as y2 minus y1. And so the total change represents the algebraic distance between the two outputs. Algebraic because it has a sign. It can be plus or it can be minus. Okay? Let me now introduce a notation called the delta notation. It is used in math and science. You will recognize this symbol, the triangle symbol. It's a capital letter, Greek letter for delta. Here it stands for difference. We saw it previously standing for discriminant, okay? Here it stands for difference. So how do we write a difference in math or science? Well, y2 minus y1 will be written as delta y, okay? And you read that as delta y. The notation delta does not specify where you have to take the difference. So it has to be understood. I have to give you an interval x1, x2, okay? So this was our first definition, total change. And let's now define the average rate of change of f over an interval x1, x2. So what is the average rate of change of a function over an interval x1, x2? Well, it's just y2 minus y1, the total change in y, divided by the total change in x, x2 minus x1, okay? And if you use the delta notation, you will write that as delta y over delta x, right here, okay? So this is a very important definition, the average rate of change. I sometimes use the acronym ARC, average rate of change. I don't believe this is used in math in general, but I found it shorter, okay? So ARC, average rate of change. Let's see, this ratio has a very clear geometrical meaning. y2 minus y1 over x2 minus x1 is just the slope of the line going through the point y1, x1, y1 and x2, y2, right? It's a slope of this line right here. It is an average, you see, between x1 and x2. I know the function went up, but it doesn't tell you that first it went down and then it went up, okay? So it's not very subtle, but it gives you an idea of the change that happened between x1 and x2. Of course, if you take x1 and x2 a bit closer together, then you're going to have a better idea of how the change happened. Okay, let's go over some examples. So I'm going to do number 1 and I will let you do number 2 and 3. You want the average rate of change of the function over the interval -3, 2. All right, so it is f of 2, that's y2, minus f of -3, that's y1, over x1 minus x2. Here we go. F of 2, what is f of 2? 2 times 3 is 6 minus 2, 4. Minus f of -3, so that's -9 minus 2, -11, divided by 5. Okay? So what is this? This is 15 divided by 5 equals 3. Now, let's think a minute. 3 is the slope of the function. Well, that should make perfect sense, correct? Because you're dealing with a linear function, you're dealing with a line, right? And it doesn't matter where you take your x1, x2, if the average rate of change represents the slope of the segment going through the 2 points, here the slope of the segment is going to be the same as the slope of the line, right? So it makes sense that in the linear case, the average rate of change is the slope of your line. Please do number 2 and number 3. Let's continue. So in this set of examples, you have a particle that moves along a line. Now be careful. This will be the graph representing the motion, but the particle is not there. It's not on the graph, right? The particle moves along a line. So this line is graduated 0, 1, 2, maybe in centimeters, maybe actually in feet right here. -1, -2. And the particle is on the line and it moves on this line. So sometimes it goes this way, sometimes it goes backward, okay? It goes back and forth. All right. Okay. So what's going on here? At t equals 0, it is at x equals 0. So at t equals 0, it's right there at the origin of the axis. The following graph represents the particle's distance from the origin during the first 7 seconds. Okay. So we see clearly that at first the particle moves away from 0, right? Its distance from 0 is increasing pretty fast. This is in feet. But then somewhere there, it's going back towards 0 pretty quickly, right? Pretty quickly. Okay, let's see the questions. What does the arc in the interval x1, x2 represent? Well, so the average rate of change when the function models a concrete situation, you will have some unit, right? So the unit for the y is in feet. And so delta y will be in feet, and delta x will be in second. Delta x will be in second. And so the ratio delta y over delta x will be in feet per second. That's what we call a velocity, okay? Speed if you want, velocity is more accurate. So the arc represents a velocity. Okay, guys, I've deciphered this problem a little bit. I'm going to let you do question 5 and 6, okay? Let's continue with the second concept of this lecture. For the second concept of this lecture, you are just given a function f. You're not given an interval x1, x2. You're not given an interval. And you're going to define the difference quotient of a function. So, how do we define the difference quotient of a function? It is f of x plus h minus f of x divided by h. That's the difference quotient of a function. How does that relate to what we just covered? Well, the difference quotient of a function is actually an arc. It is an average rate of change. It is the average rate of change of f over the interval x plus h. Okay? Why? Check it out. This is your x1 and this is your x2. So f of x2, f of x plus h, minus f of x1, f of x, divided by x2, x plus h, minus x1 minus x. And this is just the same as that after you simplify the x's at the denominator, right? So it is an arc, but the x1 and the x2 are not fixed. X is a variable, and x2, h is also a variable, okay? So this has two variables, x and h. And h, you can make it as large or as small as you want. Here, look, I've taken an example to show you how x and h are two variables. In red, you have the graph of a function. A has for coordinate x, f of x, and b, x plus h. And right here, this slider allows me to control h. As h gets small, b comes close to a. As h gets large, B moves away from A. But you can also change A. A is also a variable, right? And so you have this two possible movement right here. For example, if you're about here, right there, the slope of the blue line is about 0. So it looks like there was no change from x to x plus h. But actually, you went up and you went back down, right? Now, if you take a smaller h, then you can see that the arc, the average rate of change, will give you a better representation of the change between A and B. Again, if h is too large, you will not have a good representation of the change, but if you take a small h, you're going to have a better one. Let's go back to the note. So let's finish this lecture with two examples that I will do. I will do number 8 and 10, and I will let you do number 7 and 9. Okay? So let's start with number 8. You want the difference quotient of g, so it's g of x plus h minus g of x divided by h. So it is g of x plus h, 3 times x plus h squared minus 2 times x plus h minus 5, right? You take g of x and you replace all the x's by x plus h, minus g of x, 3x squared minus 2x minus 5, and everything divided by h. Okay, so what do we have? We have 3 times x squared plus 2xh plus h squared, I just expanded my square, minus 2x minus 2h minus 5. Okay, I'm done with the first bracket. And then be careful with this negative sign here, minus 3x squared plus 2x plus 5. Everything over h. So right away here, look, the minus 2x plus 2x, they go. Minus 5 plus 5, they go. All right, let's continue. Equals 3x squared plus 6xh plus 3h squared. All right, minus 2h minus 3x squared. Everything over h. So it is equal to, oh, and now it's the x squared that are going. X squared, 3x squared minus 3x squared, okay? And here, every term's left has an h. So I'm going to take the h out, and I have 6x plus 3h minus 2 divided by h. And finally, the h are gone, and my difference quotient is equal to 6x plus 3h minus 2. So you see, you still have your two variables in there. That is the difference quotient of g. By the way, that little step at the end, you always have to take it. This h at the bottom has to go. If you're not able to simplify it, then you have made a mistake in your work before. Now you have to be careful in the work. There's a lot of very simple basic algebra, but it's easy to make a careless mistakes here, okay? So please be vigilant. Let me do the last example. Okay, so you want to find the difference quotient of p of x, which is equal to square root of x plus h. So start with the formula, p of x plus h minus p of x divided by h. So this is equal to x plus h plus 3 minus square root of x plus 3 divided by h. All right? Now, I'm telling you here to rationalize the numerator, so you know what you have to do. You need to multiply both sides of this fraction by square root of x plus h plus 3 plus square root of x plus 3 divided by, well, the same thing, right? Square root of x plus h plus 3 plus square root of x plus 3. Now, what do you have at your numerator? Well, this is a minus b times a plus b, so it's a squared x plus h plus 3 minus b squared, be careful with the minus, minus x plus 3, divided by don't expand the denominator. I've already told you that. Never expand a denominator. Square root of x plus h plus 3 plus square root of x plus 3 right here. And how does that simplify? So let's see what we have. We have x plus h plus 3 minus x minus 3 divided by h times square root of x plus h plus 3 plus square root of x plus 3. Okay, and so what cancels here? You get the x out, you get a 3 out, and you're only left with an h at the numerator, which is great because you're going to be able to reduce your fraction and get rid of the h at the denominator. I told you, you always have to be able to do that. So what is the difference quotient of this function p? 1 over square root of x plus h plus 3 square root of x plus 3. Okay, so I hope you agree that this video is not conceptually very difficult to understand. It is only technical, and you only have to be very careful with basic algebra. Thank you for watching.